Okay, question 5, we have one of these industrial process questions, which are really quite common, and what they invite you to do is to realise that real-world situations like this are not just about equilibrium or just about rates of reaction, but they're about both, and sometimes about other issues like cost and safety as well. So it's inviting you to show that you can consider all of those and recognise that always what that results in is some kind of compromise in choosing the best conditions. So in order to make sure you get all the marks, you have to consider all the issues, the rate related issues and the equilibrium related issues, and sometimes the sort of real world related issues as well. So the thing to do is just be systematic and go through and therefore make sure that you don't miss any of those things out. So if we think about the temperature, first of all, let's think about what the effect of, say, increasing the temperature will be on the rate and on the equilibrium. And we can use that as an opportunity to bring the catalyst in as well, because it's important to mention what the role of the catalyst is. So let's talk about increasing temperature. You could talk about decreasing temperature if you want, it doesn't matter so long as you get the ideas across. But increasing temperature, what will that do? Well, in terms of the equilibrium, remember, increasing the temperature will make it shift in the endothermic direction to oppose the change, because endothermic takes heat away and therefore opposes the temperature increase. So increase in temperature will shift the equilibrium in the endothermic direction, and always put in this language of opposing the change. Explain why it goes in the endothermic direction, or at least how you know it will. So shift the equilibrium in the endothermic direction to oppose the change. Which is the endothermic direction? Well, it tells you delta H is minus 45. Remember, when it gives you that number, that refers to the forward reaction. So it's negative exothermic going forward, endothermic going backwards. Okay, so in other words, shift in the backward direction, which is bad in terms of making ethanol. So that will decrease the yield of ethanol. So that suggests that you want to have a low temperature, because the lower the temperature, the further the equilibrium will move back this way, and so the more ethanol you'll get. But of course the problem is that increasing the temperature will increase the rate of reaction, and it's worth just putting in why, because the frequency of successful collisions increases. We won't go through the whole Boltzmann story here because that's not really what it's asking, but it's worth just dropping that in there just to show that you understand why the rate of reaction increases. So equilibrium is reached faster. So you can see the problem that if you had all the time in the world, you could work at a very low temperature to maximise your yield of ethanol, but the problem is it might take you forever to get there. So you need a compromise. So a compromise requires a temperature high enough for a reasonable rate, so you don't have to wait around forever, without the yield of ethanol decreasing too much. Now we can also bring the catalyst in here because that's important. The catalyst, remember, will increase the rate of reaction, so it will mean you reach equilibrium faster, but it doesn't change the position of equilibrium. So having the catalyst there helps you get around this problem that you need to get a reasonable rate of reaction. It helps you achieve that without going to such a high temperature. And because you don't have to go to such a high temperature, you get a better yield. So you can spell that out. That the catalyst increases the rate without changing the equilibrium position. And so that means that it allows you, so it allows operation at a lower temperature. Hence giving a better yield. Okay, that's the best way to describe the importance of the catalyst, that it allows you to work at a lower temperature, and that has the particular advantage not just of saving fuel and stuff, but of actually increasing the yield. Okay, so that's the first part of the story, the temperature thing. And now we've got to talk about pressure. So again, what's really important is that we've got to talk about the rate and we've got to talk about the equilibrium position, because the pressure is going to affect both of them. So increasing pressure, what will that do to the equilibrium? Remember, that's about counting the moles of gas on each side. Because we're working at high temperature, water is a gas, as is ethanol, as is indeed ethene. So these are all gases. So you can see we've got 2 moles of gas on the left, but only 1 on the right. So increasing pressure will shift in the direction where there are fewer moles of gas, because that will tend to decrease the pressure and oppose the change, and that means shift in the forward direction. We'll shift the equilibrium in the forward direction. And again, you have to say why, otherwise they'll think you guessed. Because there are fewer moles of gas on the right. So this opposes the change. And shifting in the forward direction, that will increase the yield of ethanol. So that's good. But what about the rate? Well, of course, if we increase the pressure, the molecules will be closer together and therefore they'll collide more often. So it will also increase the rate of reaction. So that's also good, because not only will you have a better equilibrium, you'll get there quicker. So increase the pressure will increase the rate of reaching equilibrium, because the molecules are closer together, so collide more often. Okay, so that's all fine. It seems like high pressure is the way to go, because it's good for the equilibrium and it's good for the rate. But there still has to be a compromise. Why only 60 atmospheres? Why not go for 8,000 atmospheres? And the answer is because it would be phenomenally expensive to build kit that could sustain that kind of pressure, and it would also be potentially dangerous if anything went wrong. So compromise is the hugely important word in these questions, and the compromise is that the pressure can't be too high. As this would be too expensive. And potentially dangerous. Okay, and that's the full story. So you can see that the danger with these kind of questions is that you think of some of the issues but not all of them. So you need to be ready with a sort of checklist in your head of, when you get these sort of industrial process questions, have I talked about the effect of temperature? Have I talked about the effect of pressure? And in both cases, have I talked about the effect on the equilibrium and the effect on the rate? And have I brought in the catalyst, if there's a catalyst involved, as there was here? You've got to get all of those things to get full marks.